be the end of the universe? Is everything going to freeze, rip apart, collapse into singularity? Well, we're gonna find out today. So, welcome to the Fundamental Why. I'm your co-host, Carrie.
I'm your other co-host, Sahil. Today we'll be addressing two major philosophical themes. So first is metaphysics. So understand the nature of reality. Specifically here, what does it really mean for the universe to end, right? Does reality itself end, or does something continue? And then as well as epistemology, the idea of knowledge. Can we even know how it ends if this happens so far into the future?
And naturally, you guys might be asking, why talk about the end of the universe? Well, there's a simple reason why. We're going to close the loop in a sense. If you guys might remember, last episode we talked about the birth of the universe, how everything came to be, and the Big Bang all the 13.8 billion years ago. And but now we're questioning what's the universe's final destiny? And understanding the end of the universe can bring about understanding even more complex topics such as time, entropy, and maybe even the meaning of life. So now let's jump into our current proposed theories section. We're going to first start off with physics. So our first theory is the heat death theory, which is basically known as the Big Freeze. It's basically talking about how the universe is going to keep expanding indefinitely for all of eternity. And then, as you might know, as the universe expands, time progresses, and that also leads to entropy increasing. And eventually, we're gonna arrive at a maximum entropy state, a lot of disorder, maximum disorder, and the stars are gonna run out of fuel. Black holes are even gonna evaporate via Hawking radiation, and all matter is gonna be in a cold, uniform sea of particles reaching absolute zero almost.
No, so that's like a really interesting idea you talked about there. But one of my questions I have for you is, what are some of like the possible causes you think of this endless expansion of the universe?
Oh, that's actually a really good question. So you might be asking what's the driving force behind the expansion of the universe? Well, there's a simple concept called dark energy. And if you guys have never heard about that before, dark energy first came about when physicists were doing mathematical calculations, and they found out that there's not enough mass energy in the universe to explain all of that constant expansion. So naturally, they asked the question of where is this extra mass energy coming from? And that's when they came up of the idea of dark energy. Dark energy basically enacts a repulsive force across the universe, which counteracts gravity's attractive force and slowly spreads our universe apart and apart. Now, this is the first scenario where dark energy and gravity maintain their current relationship and our universe expands indefinitely. But there's also a second scenario as well, and that leads into our second theory, which is the Big Crunch. Now, in this scenario, gravity overpowers dark energy and everything collapses into a singularity, which is kind of like a reverse Big Bang in a way.
So yeah, like currently we know that the universe is actually expanding. The reason is because gravity is weaker than this like dark energy repulsive type force, right? So what makes you think that this relationship is going to reverse and like gravity is going to become stronger all of a sudden?
Oh, well, there's actually one main case where this might happen, where gravity and dark energy, the relationship is going to invert. Gravity is going to become stronger. And that's if dark energy is in an unstable state. Because right now there's not enough mass energy in the universe, but if dark energy were to decay into matter, then that will increase gravity's strength. Now, if you guys are having a difficult time understanding this, you might be able to link it with something known as radioactive decay. So if you know radioactive substances can decay over time into another type of substance, for example, uranium-239 can decay into plutonium, and just like how radioactive elements can decay into other elements, dark energy might be able to decay into matter as well. But this is all purely theoretical for now.
Okay, yeah. So that was a great like point you made there about the big crunch, potential universe contracting. Well, I want to like add on to that with our next theory. It's called the Big Rip, and I guess it's kind of in the name. You'd expect something to be like torn apart. Um, And this does tend to happen on a more of a like universal scale where we'll see that uh, dark energy doesn't just like stay at its constant like rate in terms of accelerating the universe, it actually becomes really strong. And when that happens, we're going to see that the universe expands very quickly, and then we're going to see like ripping apart of galaxies, and then eventually this will even happen to planets, and then over time atoms itself, and then space time just ripping apart. And you can kind of think of this as I like this analogy where if you like had a balloon and you're blowing into it, right? So that's currently when you're blowing into okay at a normal rate, that's our universal expansion. But imagine just like a sudden blow, like very fast, the balloon's going to like expand very quickly, and that rubber has a very high chance of tearing apart just because of the sheer force and pressure on it. So that's kind of the idea there.
Oh, that's a really great analogy of the scenario. It helped
Yeah.
me imagine it a lot better. And I know currently dark energy is stronger than gravity, but why would it suddenly become even stronger than that?
Yeah, so that's a great question, right? Like we see that the mass energy, I guess, density is like constant, right? Like involving this dark energy. So why would it ever like increase? So the idea here is it's just like purely theoretical, I guess, but there's something a form of dark energy called phantom energy. Okay, it sounds like something out of fiction, but essentially what it does, it has a special property of increasing in its mass density. So it's not going to stay constant, it's going to increase. That's going to like not just create an acceleration, but almost like an exponential expansion of the universe. But it's going to get very fast, very quickly, and we're going to see that like ripping of like our like structures in the universe, like stars, for example. But as I said before, there's no evidence behind this so-called phantom energy. But I guess we hope to like test it with different like astronomical experiments, like the LSST, where like we image billions of stars in the sky, and hopefully we can like test out this theory. Like so, yeah, that was, I guess, the big rip. And now we'll kind of move on to, I guess, yet another theory. This one's a little bit different, though. It's called vacuum decay. I do want to use an analogy to kind of explain this. It involves a little bit of quantum mechanics. So let's begin. You can kind of think of it like imagine a landscape, okay? And we have like, hills and valleys. And imagine a ball just sitting in a valley. The ball's our universe, okay? So you can say, our universe looks stable. It's just staying where it is. But now imagine there's a quantum fluctuation. Just as a reminder, that's when energy spontaneously created or destroyed in a very small time interval. So this energy is a potential to push that ball up the hill, and so now it'll come to the top, and then it's going to roll to the next valley, which could be much deeper. So now the ball comes up and then rolls down to a much deeper valley. So now the ball is in an even more stable state, right? It's just much deeper, and we would call that a lower energy state, and that's called a true vacuum, okay? Because we see that when we define vacuum states as more stable compared to our false vacuum, which we had currently in our universe, where it's stable, or it looks stable, right? So you might ask me, why is this a bad thing? Okay, our universe is just more stable now, right? Like that seems we feel more safe, I guess. Right? But no, that's not the case because at least quantum fluctuations happen at a very small point in space. So if it happens at one point, well, the universe favors this stability, so it's going to spread. It's going to become a bubble and expand at the speed of light, consuming everything in its wake. You can think of it, and this would rewrite the laws of physics as we know it because the laws of physics are dependent on like the energy state that we have of the universe. So you can imagine this bubble just coming at the speed of light and consuming everything, and we wouldn't even see it coming, right? Because it's traveling that fast. So that's the idea of the vacuum decay. It's unpredictable because any quantum fluctuation could just create this bubble wiping us all out, before we even know it. So I know it sounds like a crazy idea, but there's a small chance of that occurring, right? I guess quantum mechanics always tells us that, right? So yeah, now those are all our, I guess, physics theories we had, and now we'd like to move on to like um our philosophy section here. So let's hear a bit more of our analysis on like the big bounds and eternal recurrence.
Yeah, so first I want to talk about this idea about eternal recurrence. It connects with a theory I mentioned previously, the Big Crunch. So uh, this idea actually links with cyclic universes where we have a big crunch, everything collapses together into a singularity, and then we have something kind of like a big bounce where everything suddenly spreads out, expands at higher than light speeds, which kind of connects back to a big bang in a sense. And this keeps repeating and repeating, and that's what we call a cyclic universe. So there's this philosopher called Friedrich Nietzsche, and he asked his students one time this famous question. So, What if the universe ended and began and repeated endlessly? Would you live this life again? This is really interesting because it connects with things. It connects with the concept of the fear of the unknown because the universe is going to be different each time it repeats due to quantum fluctuations. It might not be the same universe as we currently are in right now. It's going to have a different starting condition each and every time. And we don't know what that starting condition is going to be. It's up to chance. And so we might not know if it might benefit us or it might harm us. So that fear of the unknown might make you not want to live this life over and over and over again. But there's also that hope in some people where they could be living a better life, and that hope might empower them to continue to relive the life.
That's a great philosophical implication of the big bounce. I want to do also connect it to a bit of physics as well. This is a nice connection to one of our previous episodes on the nature of time, and I want to talk about the arrow of time. Right? Previously, I told you that we define time as in correspondence with entropy increasing. So as entropy increases, time moves forward. Right? But now we've talked about the big crunch theory and the big bounce. Right? So I want to focus on the big crunch idea, where our universe is contracting. Well, that actually means that energy and matter are kind of are becoming more ordered, right? Because they're coming closer together, and so we can see that the entropy is actually reducing in that case, right? Because the distribution of matter and energy is they're coming closer together rather than disordered and spread it apart. So now, if our entropy is reducing, would you say time is now moving backward, right? If I were to imagine myself living in that universe, and we just see stars coming closer, I would still feel like time is moving forward for me in the sense that I won't suddenly start reversing my actions all of a sudden, right? Just because the universe is contracting, entropy is reducing. So I just feel like maybe when we think of the big bounce, like thinking of uh, time as being in correspondence with entropy increasing might not always be like the best definition, right?
Mhm.
Yeah.
That's really interesting to bring about. As you know, we mentioned previously in our time episode, we connected entropy with time. And now I want to link back to another philosophical concept about nihilism, more specifically cosmic nihilism. For those of you who don't know, nihilism is basically the belief that none of this is real, we're all fake, and there's no meaning in anything. And you might see that we've been talking about the end of the universe, and it might bring about some sad emotions that everything's going to end one day, nothing we do ever matters, and that it's all meaningless because we might not even be able to predict our end if you believe in vacuum decay, where our end might come from random fluctuations of energy and it might happen any second now.
Yeah.
But there's also another way to look at this and look at it with a little bit more positivity, because you might say that an ending brings about meaning to something. For example, if you look on your memories, we look fondly on our memories because it reminds us of something that once happened but has now ended. And also, we don't really understand our universe or even ourselves or reality enough to be able to say for sure that it's life and the universe is devoid of meaning just because it's going to end one day.
Well, I think that's a great interpretation there that, we need to truly understand our reality and our universe before coming to those like conclusions that life is meaningless, right? So now I do want to talk about another connection. I feel like vacuum decay is a nice place where we can talk about because of its unpredictability. So the topic I want to look at is called like determinism. So as a reminder, determinism just means that all events can be determined by prior causes. So let me give you an example. Let's say we had like a computer with infinite computing power, and we knew the initial conditions of the universe, like the starting position of every particle, the temperature, etc. Right? Then, like according to determinism, we'd be able to mathematically calculate every instance in time. So then that would be like, okay, we know the future, I guess you could say, right? Because just by knowing what happened like that, like 1 second before, for example, right? So that's the idea of determinism that like everything's predetermined, but not by like some godlike entity, but mainly by like physical laws and mathematics. That's the idea. But I feel like vacuum decay, right? Connecting it back to that is a bit different. It's based on quantum mechanics, a probabilistic theory. So it's so sudden, right? Like that bubble can just appear and start expanding towards us, and there's no like way we can somehow calculate it because it's based on a quantum fluctuation, right? That is just inherently random. So in that case, maybe our world is not really deterministic, but rather probabilistic, like what quantum mechanics has to say, and we can see this through like vacuum decay, right? So now I feel like now would be a good time to like move on to like our discussion section.
So, we've talked a lot about the end of the universe, and I want to start us off with a question about the laws of physics. So, we like to think about the laws of physics as absolute, never changing. But we've been talking about vacuum decay quite a lot, and vacuum decay tells us that the laws of physics can actually change. So, Sahil, were they ever absolute to begin with?
Okay, that's a great question. I think
Mhm.
it would be great to start by like defining the word absolute. At least when we think of absolute, you can think of it like as were we like discovering these laws? Were they like a fundamental like part of our reality, like in the bedrock of our reality, like rules written, or is it something that like, as it something we describe of the universe, right? Like it's almost like I see a pattern, I'm like, okay, I'm gonna describe that pattern, right? Like so there's like two different ways of thinking of absolute. I feel like let me just take the perspective of the first idea I came up with where like time is or sorry, not time. I meant like any like physical law is inherently discovered, so it's like part of the universe. If we think of it like that, um, it doesn't really go well with the vacuum decay idea, right? Because like it just rewrites the laws of physics, so like they were never absolute. You can say in that sense where um, we just changed those laws that we thought were fundamental, right? But I feel like here's my idea. I feel like what if these laws of physics are just dependent on the energy state of our universe? So like the universe can keep like going to lower and lower energy states with each fluctuation. Well, imagine there's more and more that can happen. But what if we get to the lowest stability state, like the most stable, and it can't go below that? If we were to think that there's some such state, then I feel like once we reach that state, then the laws of physics are absolute because they can never like change again. So it feels like that's like my idea there. So what do you think, Carrie?
I think that's very interesting. So
Yeah.
right now we're currently like we're looking at the laws of physics, but we're not looking at the true form yet. In a
Yeah.
sense, like if they were to descend to the
Yeah.
actual lowest energy level, we would see their like true form, and that's when they would be completely absolute. I think that makes quite a bit of sense, actually, I guess. But in my opinion, I don't really see the
Yeah.
laws of physics as like discoverable things, like
Yeah.
actual physical things in our universe, but more as things we humans ourselves came up to describe patterns or relationships in nature. Like, for example, gravity we see as just the relationship between like the attraction between two pieces of mass. And think in this sense, they aren't really absolute because they're only as absolute as the things they describe in a sense. If the things they describe don't change, then the laws of physics will never change in my perspective.
Ah, so you're saying like the laws of physics are kind of dependent on like what we see in nature. I think that's like a great perspective there as well. I mean, the reason I thought it was absolute, at least I'm still kind of leaning toward that idea is because like even if they change, like imagine we have like a large rule book, and for each energy level, we have a law, like we have like certain laws of physics. So we can just say we have different groups of laws, and we just have to choose the right group. So I feel like you can have this like you can generalize to that highest level. That's what I'm kind of thinking there in terms of like them still being absolute in that sense. But I think you still might be right because our senses itself might be limited, right? Like how we see and like how we what we feel, all that stuff is like only for us humans. But imagine, as it says, there's like there'll be some like alien species, for example, that's more advanced, and they'll be able to have maybe different laws of physics, right? So what? So I think I'm slowly starting to agree with your idea that the laws we have right now aren't like absolute fundamental laws, but they can like change, right? Based on like what we see, we might need to refine them sometimes, or just our own fundamental limitations, right? So yeah,
Yeah, I think that's interesting because our biological limitations might actually affect what we
yeah,
are able to see, like come up with. And if we were like more intelligent in a
yeah.
sense, we might be able to see past the current laws of physics and maybe even come up with new systems that might be absolute in a sense. It might be because of our limitations that our laws are not that absolute in a sense.
Yeah, so that's just like I guess we can kind of like maybe lean more to the side of like the laws are merely descriptors, but like not absolute, right? So I think that's I guess a great discussion we had there. And now I kind of like to move on to our next question, which is, um, you know how at the end of the universe, right? It might just be beyond our own observation and comprehension. Right? It's so far in the future, like, and so like now the question arises, like, does it even is there any value in even understanding the end of the universe?
Yeah, that's a great question because most of the theories we talked about for the end of the universe, they happen
Yeah,
billions and billions and billions of years. We might not even exist as a human race at that point, and it might be hard to see the impacts of understanding something so far away right now in the short term. But I think sometimes it's also necessary to look at maybe long-term effects and how if we slowly start to investigate something as obscure as the end of the universe, we might come across like discoveries that we didn't mean to find out, and it might help us lead into new discoveries that are unrelated even to the end of the universe. And I'm sure,
yeah,
because of your history in physics, like past discoveries, that a lot of them were made accidentally, even
exactly.
or
Yeah.
like through mistakes. And I think overall, it will still be of value to us because we can discover other things we didn't mean to discover.
I think I completely agree with that perspective, right? That we don't ever like at least scientists like in academia or all those researchers like that the public commonly thinks as like what are they doing? Like their research is too abstract to ever have a real impact, right? These researchers don't really go with the mindset of like, oh, I'm gonna study this to discover something new. Right? They tend to happen like I guess as you said accidentally because physics is just so foundational, right? Everything's based upon it. So by finding these new principles, there's so much potential that we can't even imagine, right? And like a nice like, analogy, I guess in history we can think of it as if you go all the way back to like the 20th century where you had like physicists like Einstein and Niels Bohr were all creating like the framework for quantum mechanics. They were just studying an electron, like to understand, okay, why do electrons behave as waves, particles at the same time? That's all they were asking. They weren't like thinking about all these applications that come up. For example, like superconductors and electronics, and how much quantum mechanics has changed that. So in the sense, I feel like I would agree with you that in the same way like that they found breakthroughs in quantum mechanics. If we were to look at the end of the universe and try to understand it, there might be unintentional, I guess, impacts and consequences for potentially more breakthroughs in the future.
Oh, yeah, that's
Yeah,
nice. I like to see that we have a common view on this
yeah,
topic.
likewise.
I have a question for you.
Sure.
So I was pondering about like how important might something like this be in a sense. So do you think we should be putting resources into studying this concept, or should we prioritize more like short-term research, like perhaps like climate change, how to combat that? Like, what do you think
Yeah,
about
that's a really common question. Like, I guess like commercialization of science, right? Like, are we gonna like use it for an impact? Science, like, do we do science just for to feel more benefits or for curiosity, right? So, what I like to say about this, I feel like although I'm a bit biased being like okay put all our resources for long term, I still like honest I think with a more like my opinion would be that I think we need to balance. Okay, like of course like short term is important. We can't just like ignore like the new viruses that come up maybe or like the climate change that's affecting us, right? Like that's still important to address, but at the same time I feel like we shouldn't be too short sighted and just put all our money there and like ignore any of these like abstract possibilities, right? So of course, put some money, for um, short-term needs, but at the same time, it's still important that we prioritize like long-term or like long-term impacts that potentially scientific theories can have. So if we were to pursue, for example, the end of the universe, people, like although you might be in your lab like alone and no one's going to know what you're doing, no one's going to understand what you're doing, but you can still have an impact, right? It's like together many scientists push that field forward, and I feel like those new discoveries you can potentially make will have an impact in the long term. So,
Yeah,
so yeah,
because we don't know what might happen from
exactly,
that research, and we don't want to like completely cut off one of
exactly,
those
right?
paths. We want
Yeah,
to support them balanced equally.
yeah.
I
So
think that wraps up the discussion section pretty well. Those were some
yeah, a
very
great
interesting
idea. So
answers. I think we can move on to our wrap up and even
yeah, the conclusion.
teaser for next episode.
Okay, so yeah, now I'd just like to summarize a couple things that we talked about today. So for our physics theories, we talked about, the big freeze, the big crunch, the big rip, as well as vacuum decay. And then we kind of moved on to some more philosophical implications, looking at, what are some implications of the big bounce or slash the big crunch, as well as cosmic nihilism and like thinking about the meaning of life there. And then lastly, determinism. And then for our discussion section, we talked about the absoluteness of physical laws now in the face of vacuum decay that kind of complicates that, And we kind of did agree about like physics laws as being more descriptors. And then, for our question we just had right now, we talked about, balancing resources for short-term and long-term needs, and how we agreed that it's still important to pursue such, like questions that seem like abstract and almost like has no meaning, right? So yeah, that's kind of what we looked at today.
And we've talked about current proposed theories, popular theories currently, and then we went on to our own opinions about the end of the universe. So now it's time for me and Saho to ask you guys a question about the end of the universe. So, what do you guys believe to happen at the end of our universe? A, everything is going to freeze to death. We're going to run out of useful energy and maximum entropy. B, you might believe in the big crunch even, where everything collapses into a singularity. Or C, everything rips apart, dark energy gets even stronger than it is right now. Or even D, where we have vacuum decay, the instant annihilation of everything. Or E, we have God. So he would decide everything for us, and we don't have to worry or ask about any of these questions. So we've seen the beginning and the end of our universe, but if our universe is just one of many in the endless multiverse where beginnings and endings might not be so final after all, and where reality itself might be challenged, then what does that mean for us, humans, and meaning and anything actually? Well, you guys will have to find out next time on the
Nice.
Fundamental Why. So
So,
like
like
and
and subscribe,
subscribe and
and
see
see you
you all
all
next
next time.
time.